Alright, this is the practice problems, activity 1.1.5 for gears, pulley drives, and sprockets. So let's begin. So this one gives you a simple setup where it tells you about gear A, gear B, and gear C. Alright, so gear A, this is going to be a really pretty simple one. You have 3 gears. You have A, where N is equal to 8, and that is meshed with, the problem is getting the size, so we'll just draw it bigger, because gear B has 24 teeth. And then gear C will be a little bit bigger than A, but not as big as B. Now, speaking of which, we should label these. This is A, B, and C. Done. Let's move on to the next one. So the outputs at C, what's the gear ratio? The gear ratio is equal to, since all we have, excuse me, all we have is the number of teeth. Then that's the equation we have to use. So we just substitute and solve, literally number of teeth out over number of teeth in. And that's our final answer, 2 to 1. But we don't write it like that, we have to write it as a ratio. Okay, so now we're talking rotational speed here. So the formula for this is the gear rotational speed is related to the gear ratio, of course. Okay, so our gear ratio for between A and C, we know from before, is 2 to 1. So this will be equal to the rotational speed in, which is 60.0 RPM, over the rotational speed out, which is C at C. So we just solve for C, and that will be our final answer. So do a little cross multiplication here. So now for question 4, we want to know if we need this amount of output torque, that's the required torque, what should be the input torque at gear A? So again, it's all related to the gear ratio. In this case, it's tau out over, I always do that, tau in. In other words, the torque out over torque in. So between A and C, again, we have the ratio of 2 to 1. And our output torque is going to be 150 foot-pounds over the torque at A. Okay, so again we solve for the bottom one, the missing variable. Torque at A will be equal to 2 times that, will be equal to 150 foot-pounds. And so when you solve for that, turns out the torque at A needs to be 75 foot-pounds. Okay, so now we have a compound gear train. That's the one where you have gears on sharing shafts. So part of the trick of this is reading this and being able to make sense of it, which is why sketching is very important. So basically what we have here is gear A has only 10 teeth. Let's call it gear A, and it's meshed with gear B. Okay, it's got 20 teeth, so I'll draw it much bigger. I don't know. this is not to scale. Now I'm going to label it up here because on the same shaft as gear B is gear C, which has only 16 teeth. And I'll label the teeth soon. Now gear D is meshed with gear C, and that's going to have, well, we don't know what kind of number of teeth it's going to have, so I'm just going to draw a circle to represent gear D. And to make this look nice, let's erase this line right here, because gear D is going to be sitting right on top of that. Okay, so let's label this gear D. Now we can start putting in some of our known gears. So for gear A, the N value is 10. Gear C, N is 16. Gear B is 20 gears. And gear D, we just don't know. We don't know. So I guess I'll put a question mark. Okay, so now we're talking torque, and it's going to involve our gear ratio. So our gear ratio is equal to the output torque over the input torque. And we know we want the output to be 500, and we know from above that gear A gets 100 foot-pounds of torque, and we know something about the RPMs. We'll come back to that later. And so the gear ratio is what we're trying to solve for in this case. So 500 is what we want out, foot-pounds, and 100 is what's going in. So turns out the gear ratio is literally 5 to 1, so we can just put that here. And our final answer will be 5 to 1 gear ratio is what we want. Okay, so we have an output torque of 500 foot-pounds. So we need to know how many teeth should gear D have in order to get that. So the gear ratio, of course, is equal to, now we're talking about number of teeth. So N out over N in. Now the gear ratio, we solved it earlier. It's a 5 to 1 ratio, but we didn't incorporate anything about the teeth. When you get the gear ratio, this is a little complicated here, but the gear ratio, when you're figuring out teeth, or using teeth, involving teeth, is going, for this one, is going to be equal to, since the compound gear setup, we have to take into account, it's going to be A is meshed with B, but then C is meshed with D. So we had to basically find those two gears and then multiply them together. The gear ratios multiply them together. In other words, we need to find the gears of the number of teeth of B over A, because it's out over N. Take that and multiply it by the number of teeth at D over the number of teeth at C. And that will be equal to 5 to 1. Okay, so let's just kind of rewrite that and actually substitute in all of our knowns. So the number of gears, the number of teeth at gear B is 20, and the number of teeth at gear A is 10. We don't know D, that's what we're trying to solve for, but we know that at C there are 16 gears. Okay, so when we solve for our unknown variable, it turns out that the number of teeth that D should have is 40. Okay, pulleys and belts. So we have a new system here, pulley A moving at 1500 RPM, and we have a diameter of 15 inches. We got three other pulleys, B, C, and D, all of different sizes, attached to a single output axle. Speed and torque output are changed within the system by moving the drive belt between pulleys B, C, and D. This is a very common setup for machines that require different amounts of torque for different applications, drill presses and stuff like that. But you look at this, and the hard part is, what are they explaining here? So the sketch starts out with pulley A. So let's draw a circle. And this is my first pulley. I might as well have lots of room here, so 1500 RPM, and the diameter is 15 inches. Now the confusing part, we've got B, C, and D all of different sizes, all attached to the same output axle. So in other words, this is the axle that's going to be driven. And here it is. So we have 3 different pulleys. We got this one, we've got this one, and we've got this one. And we'll just call them pulley B, C, and D. Okay, and they're connected with a belt system that goes around. And it comes back around the bottom here. Okay, so they'll turn, and you could change the belt to be, right now it's on B, but you could change the belt to be on C or D if you need to. So, looking at our questions, we need a speed of 1750 RPM when the drive belt is connected to pulley B, so what should the diameter of pulley B be? Now, the only thing we really had to work with is RPMs and diameter. So we want to know the output diameter, which will be in a ratio with the input diameter of, so that'll be A. And we are talking rotational speed. And this is the upside down one, so rotational speed in divided by output rotational speed. So our diameter out will be B, and our diameter in is at A, which we know is 15 inches. We know our input speed is 1500 RPM, and our output speed is 1750 RPM. So we do the cross multiplication and we solve for the diameter of B, and so when we do that, the diameter of B will need to be 12.9 inches. Alright, so now we have a different pulley. We want a different RPM, pulley C, and we basically do the same thing here. So they move the pulley, they move the belt to pulley C. So we use the same exact thing. It's basically the same exact setup. Except now, of course, our output is at C. And our input is still 15. So our output, though, is going to be 2000 this time. And that's it. That's the setup. So now you solve for C, DC, diameter of C. And when you do that, diameter of C turns out to be 11.3 inches. Okay. Guess what? Same exact thing. So our D out over D in is equal to W in, W out. Of course, this time we want the diameter of D over that 15 inches. and our 1500 RPM over. Now we want the output to be the 3250. And so that's basically the setup. So when you solve for the diameter of D, you end up with 6.92 inches. Okay, onto sprockets and chains. There's only one question here, and honestly the hardest part is understanding what they're talking about. So when you read this, what it's describing is a manually opened door, and the operator, the person, basically needs to pull on a chain to open it, a looped chain. So what we have here is the person pulls on a chain that's attached to a sprocket that has 22 teeth, and that chain just sort of dangles down there, and so the person can just pull on it just like that and it'll open up the door. Okay, so now on the same axle as this is, and this is the confusing part in my mind, is there's another 22 tooth gear right behind that. Alright, I guess I'll just put that there, right behind that, and that is hooked up to our much bigger 48 tooth beast that is turning and opening the door, or I should say opening the door. So we're going to have a chain that goes from there. So so in other words, I don't know if I captured this, but there's the 22 tooth sprocket in the front, the 22 tooth sprocket in the back, and that one in the back is hooked up to the 48 tooth sprocket via the chain. Okay, so that's the setup. So all we want is the overall system gear ratio. So gear ratio for a sprocket and chain. In this case, we have the number of teeth, and the number of teeth out, the output, divided by the number of teeth on the input. And so our gear ratio is going to be equal to 48 teeth as output and 22 teeth as input, and that is the final answer. So, well, I mean, we had to simplify it. 2.18 to 1. So I do think the hardest part of this problem maybe was understanding what they were explaining. Other than that, that's how you do it. And I believe that's it. Yep.